In this video, we're going to take a look at section 2.1 on functions. Right. So before we talk about what a function is, we have another definition to address first, but it's a very broad, generic definition that isn't really all that helpful. A relation is anything that relates two variables to one another. There's no other qualifications besides just having two variables somehow being related. That makes it a relation. So some common examples of relations would be graphs, tables, and equations. So on a graph, when you draw a picture on a Cartesian coordinate system, like a parabola or a circle or a line, you have points on that drawing, and those points have an x coordinate and a y coordinate. So each point is connecting an x value to a y value, so that makes it a relation. It's showing you how the x and y values are related to each other. A table does the same thing, except in tabular form, so it would look something like this, and you might have like 0 going with 3, 2 going with 1, etc., etc. This is a relation because it's showing you how the x values connect or relate to the y values. And obviously equations would be another example of a relation when you have an equation with two variables. So like y equals 2x plus 3, that's relating an x value to a y value, maybe not just one, but infinitely many x values to y values, but it's showing how the values of x relate to the values of y or vice versa. So it's a very broad definition. In fact, it's a little too broad, because there's a lot of things that can be relations, and many of these relations can be very poorly behaved, difficult to study, difficult to exact a structure out of. And without any kind of structure, things become really difficult to study. You can't have rules on a group of things that don't behave well. So we want to filter this a little bit to get something that at least has some reasonable behavior. That way we can start to study it a little bit more in a structured way, so we can have rules and things to apply to it. And that's where the idea of function comes in. So a function is any relation in which for each value of x, so more technically I should say for each value of the domain, but x often represents the domain, the values of the domain, there is only one corresponding value for y, which, again, I should technically say the range. So presuming that your independent variable is x, your dependent variable is y, then x would be the domain, y would be the range. And you could just say it like this. For each value that you could choose for x, there's only one possible answer for y. That's what makes something a function. So it's a nice characteristic for a relation to have. So when I pick a number for x, I don't have to worry about tracking down 5 different answers for y in the table or in the graph or wherever. I know that if it's a function, when I pick a value for x, there's only going to be one possible answer for y. That's what makes it a function. All right. So it gives it a nice behavior while at the same time not making it too simple either. And so I had a math professor one time that told me that the trick with math is to come up with these definitions that give something a nice behavior without over-defining it, because if you over-define it, it makes it too simple and not worth studying. So you have to kind of strike a balance between, we don't want it to be too awful, but we don't want it to be too easy either, because then it's not interesting if it's too easy. And I think the definition of a function does a really good job of striking that balance, because there's going to be a lot of different kinds of equations that are functions that are really still quite interesting and challenging and worth exploring, taking the time to actually do things with. But at the same time, we're filtering out relations with this really poor behavior of picking a number for x and getting multiple answers for y. Those are really much more difficult to manage. And so again, we're giving our equations that we're studying a nice property without making it too simple and not worth really looking into. All right, and that's what function does. Okay, so this whole section is about, for the most part, it's about functions. How can you tell when something is a function or not? And so we're going to go through those three relations I identified earlier. There are other types of relations, but the three we're going to focus on are graphs, tables, and equations. How do you know when a graph is a function? How do you know when a table is a function? How do you know when an equation is a function? All right, so for graphs, this is one of the easiest topics in the entire course. Now, we just got through chapter 1. There's a lot of tough material in chapter 1. Honestly, chapter 1 is one of the hardest chapters. It might seem a little backwards because you would think that it should start off easy and kind of work its way up. But in my opinion, chapter 1, because of, not that any particular topic is the most challenging, but just because it covers so much material. It's a really challenging chapter, and some of that material is pretty difficult. Anyways, I'm getting sidetracked. So the vertical line test is going to be one of the easiest things that you will do in this course, right? If there exist no vertical lines that cross the graph more than once, then the graph is a function. But if you can find just one vertical line, now vertical goes this way, right? If you can find just one vertical line that crosses the graph more than once, the whole thing is ruined. It's not a function at that point. So that's what you're on the hunt for. Can you find a single vertical line, or more than one? It doesn't have to just be one, but can you find a vertical line that will cross the graph more than once? If you can, it's not a function. But if you can't, if no matter where you try to place a vertical line, it never crosses the graph more than once, then the graph is a function. All right, so that's the vertical line test. So it's really kind of a visual problem. I mean, so there's no calculations to do. It's really just about visualization. So you can just kind of visualize when you look at these graphs, visualize vertical lines being drawn through the graphs. So this is one of my favorite things to do, because when I'm recording this video, it's not during the normal course of a semester, so I'm not really teaching the class right now. But normally when I'm teaching this material in class, if face-to-face, we've just finished chapter 1. They just get their test back. And one of the topics from chapter 1 that a lot of students struggle with is section 1.3, which is mostly about circles. And so I like to revisit that topic here to help illuminate why that topic was difficult, right? So this graph is the graph of a circle. Is this graph a function? Well, let's try drawing vertical lines through this graph and seeing how many times can a vertical line cross this graph. And there's plenty of places you could choose to draw this, but I will try to draw it right here. And I'm sorry, it's really hard. I should be wearing my glasses, I feel like. So here's a vertical line. How many times does that vertical line cross the graph? It crosses the graph twice. Right? Crosses it once here, and it crosses it once here. And I kind of did a bad job of marking that second one, but it crosses it twice. And so this is not a function. That's all there is to the vertical line test. Now I'm going to explain why it works, but that's all you need to be able to do, is remember that if I can draw a vertical line that crosses the graph more than once, it's not a function, which is why circles were so challenging back in chapter 1. They are difficult to manage. They're difficult to figure out because they are not functions. They have the property that if you plug in a number for x, you will often get two different answers for y. It makes them hard to work with. It makes them hard to graph. And that's why they were such a nuisance back in chapter 1. Right? Now, why does this mean it's not a function? So remember, to be a function, when I pick a number for x, there can only be one possible answer for y. That's how we know when something is a function. What we're doing with the vertical line test, when you draw a vertical line, and I tried to make it as close to this number as I could, but it doesn't even matter what the number actually is. When you're drawing a vertical line, you're choosing an x coordinate. I tried to choose 1, but you can see I'm a little off the mark, but let's just pretend like I drew that line through where x is equal to 1 on the x-axis, right? So 1 is like right here. So I'm drawing this vertical line through 1 on the x-axis. So I'm choosing x equals 1. And you don't have to actually pick a number for x when you're drawing a vertical line. By drawing a vertical line, you are choosing a number for x. And it doesn't even matter what number you're choosing. Just remember that vertical lines are representing a choice for x, for an x value. The number of times it crosses the graph are the number of different answers that you can have for y when x is equal to that number, right? So when x is equal to 1, there's two different y coordinates here. So that's two y's with the same x coordinate. That's one x with two different y's. That's why it's not a function. To be a function, one x has to go with only one y, right? Hope I'm saying that right. So let me think about that wording again. So when I pick a value for x, there can only be one possible pairing of a y value with that value of x, right? So when I pick a value for x, there's only one possible, connection. I don't know. I feel like I'm having trouble describing it now. When I choose a value for x, there can only be one possible y value that goes with that value of x. There, I feel like I can live with the way I just said that. Okay. And I don't know what these y values are, right? They're like a little bit less than 2, but I don't know. It's like 1.9 or something. But we have positive 1.9 up here. We have negative 1.9 down here. So there's two different y values that go with that one particular value of x. That's why the vertical line test works. The vertical line you draw is choosing a number for x. The number of times it crosses the graph are the number of different corresponding values for y for that given value of x. And if there's more than one, it's not a function. All right. What about the second graph we have here? Is this a function? Yes, right? So I can draw a vertical line anywhere on this graph. So let's just draw one here, for example. How many times does it cross the graph? Once. But you shouldn't just say, okay, well, I tried one line. It only crosses once, must be a function. You have to be certain that any vertical line you could draw will only ever cross the graph once or possibly not at all. But you want to make sure that no vertical line can cross the graph more than once. So you want to check it in multiple spots. So don't just imagine one vertical line. Imagine all of them, really, is what you want to do, all the possible vertical lines. But no matter where I draw a vertical line on this graph, and some of these are not quite as vertical as I would like, it will only ever cross the graph once. And so that means this is a function. There is no vertical line that crosses the graph more than once. So when I choose this value for x, there's only one possible answer for y. When I choose this value for x, there's only one possible answer for y, right? So there's one y here, whereas this one, we had two y's, right? That's where you run afoul of the definition of a function. So parabolas are functions. And we're going to actually study graphing parabolas a little bit more in chapter 2, but also in chapter 3. We're going to spend some time on parabolas there. And just because they're functions doesn't mean they're necessarily easy. Parabolas, there's more to graphing a parabola than, for example, graphing a line. Graphing a line, you just need the slope and the y-intercept. The parabola has a little bit more going on, so it's a little more work, but it's going to be probably easier than you found circles to be. Okay. What about tables? How will I know when a table is a function? So this one's a little more obvious. If there are no repeating values in the domain, in the values of x, then the table is a function. All right. So you want to look for repeating values of x, and we'll talk about why that matters when we look at these examples. All right. So in this table here, you look at the x column. We have x equals 4, and then we have x equals 4 again. It's listed twice. Now, why would they want to list the same number twice for x? The only possible reason for doing that is that there are two different answers possible for y. So if I were to choose x equals 4 in this relation here and ask you what is the answer for y when x is 4, you would have to say, well, there's two different possible answers. Y could be 13 or y could be equal to 1, right? So I'm choosing one x and I'm getting two different y's. And so that's why it's not a function. And the red flag there, the indicator that that will happen, is having repeating values in the x column. If values of x are being repeated, it's because there will be more than one answer for y when you choose that value of x, therefore making this not a function. Right? So this table is not a function. And it doesn't matter how well it behaves other places. You might say, well, wait a minute, but when x is 9, there's only one answer for y. That doesn't matter. It's a case of one bad apple spoils the bunch. Right? If there's just one example where it behaves as not a function, the entire relation is labeled not a function. A good example of that with a graph would be something like this. I call it kind of like the Superman here, like this, right? So like an S shape, right? Here, drawing a vertical line only crosses once. So you might say, oh, that actually, here it's behaving like a function. And I would agree with you. In this area, it behaves like a function would. Here, it also behaves like a function, right? This vertical line only crosses the graph once. But in the middle, we actually have vertical lines that will cross the graph 3 different times. That means when you choose this particular value for x, whatever, I don't know what it is, but whatever this x coordinate is, there are 3 different possible answers for y. And it doesn't matter that it worked nicely here and here. This ruins the whole thing, right? This is not a function now, right? So all it takes is one bad apple to make it not a function. So keep that in mind. All right, what about this table over here? Now this is intentional. They're trying to throw you off. Sometimes on some of these problems, they are trying to trick you. And this is one of those cases, right? They are repeating the y values. So you have -4 for y every single time. But is this a function? It doesn't matter if the y values repeat. What matters is if the x values repeat. That's what will indicate whether it's a function or not. And because no x values are repeating here, right? No repeating x's, this will be a function. And the reason is, when you pick a number for x, how many answers can you get for y? So if I pick x equals 2, what is it possible for y to equal? Well, -4, that's it, right? So 1x, 1y, right? That's how a function should behave. You pick a value for x, there's only one possible answer for y. What about when x is equal to 7? What can y equal? Well, -4. Yes, it's the same answer as before, but it's still satisfying the definition of a function because, again, I pick 1x and I get one possible answer for y. It doesn't matter that it's the same answer again, it still satisfies the definition. For each value of x that I could choose, there's only one possible answer for y. And so it's a function. So it doesn't matter if the y values are repeating, it only matters for tables if the x value is repeating to determine if it's a function. Now, there might be sometimes something I'm kind of paranoid about is if other math teachers are watching and they might be kind of critical of my explanation for functions. Now, I'm kind of teaching out of the book that I'm teaching, Dugopolsky, and this is sort of his approach to the topic. But other textbooks might, I don't want to say make it more complicated, but they might delve a little deeper into the concept of functions because you can ask if one variable is a function relative to another variable. So you can switch it around. So what I could ask here is y a function of x? And the answer here is no. But is x a function of y? Yes, right? So it kind of depends which variable you make your independent variable and which variable you make your dependent variable. And that can change the answer. Here, y is a function of x, but x would not be a function of y. But this textbook doesn't really explore that concept. And so that's why I'm not really addressing it. That's why I'm leaving it out. And if you're one of my students, if that confused you what I just talked about, don't worry about it. In this textbook, I believe there's not really any problems that address this. We're always concerned with whether y is a function of x, and that's it. We're not trying to see if we flip the variables around, if it makes a difference or not. So we don't really explore that concept here. So for all of the rules I'm giving you, it's to test whether y is a function of x. That's what it applies to. So if you're not in my class, if you're taking college algebra from a different teacher and they're using a different textbook, they might be exploring that aspect of the topic and I'm just not getting into that any more than I just did. So you're kind of on your own. You might need to find another video that maybe addresses that concept a little better. All right, for equations, how can you tell if an equation is a function? So now admitted that I might be a little nervous about other math teachers viewing my video and like criticizing my explanation. And this is definitely one that I would be really worried about people being unhappy, other math teachers being unhappy with this explanation. And because I'm unhappy with it too. It's cheap. It really is only applicable for college algebra. So this is not like a rule, like a universal rule that would work in any math class for any kind of equation. So it's just based on the equations that we will be working with. This rule will get you through the class basically. But in addition to this sort of shortcut, because what I find is some students like the in-depth explanations and trying to understand the concepts, the context, the background information and all that. Some students enjoy that and like that and appreciate that. But other students, I understand, don't really care about any of that. This is their last math class. They're just here to get a passing grade, and they don't really care about, digging any deeper than they have to. And I respect that. So I do try to accommodate both types of students. So for the type of student that just wants to get the right answer and doesn't really have an interest in the concepts or the ideas or exploring this any further, that's what the first paragraph is for. It's for those students. So this is sort of a shortcut to help you identify if an equation is a function or not. If there are now this is kind of a flip here, because with graphs, we're concerned about vertical lines, which are values of x. For tables, we're concerned about repeating values of x. But for equations, we actually need to be concerned about the y variable. So if there are no y variables inside an absolute value or being raised to an even power, then the equation will be a function, no matter how awful it might look. As long as y is not stuck in an absolute value, as long as y is not being raised to an even power, it's a function. It'll be a function, because that's the only two scenarios that you will be given in this course that would cause it to not be a function. However, for students that are maybe more interested in a, more in-depth understanding the concept type of approach, my recommendation here is just to try conducting experiments by plugging in a number for x and seeing how many answers you get for y. So take the equation they give you, plug a number in for x, and then solve it for y. If you only get one answer for y, that's an indication that it's a function. It's behaving like a function should behave. But you shouldn't just draw that conclusion from one experiment, right? So you can't just plug in one number for x and assume that tells you everything you need to know about the function, about the relation. We don't know it's a function yet, right? You want to test it multiple times. Test it with a negative number, test it with a positive number, test it with a big number, a small number, just to make sure it doesn't do something different in those scenarios. But usually, after one or two tests, you'll get a sense of what the equation's capable of doing. And if it's only capable of giving you one answer for y every time, it's a function. If you get the sense that the equation could produce multiple answers for y when you solve for y, then it's not going to be a function, right? So experiment, plug some numbers in and see what the equation does. And that will tell you if it's a function or not. This is really the best way, because this is applicable in any math class at any time. If you ever need to know if something's a function, no matter what kind of equation you're given, this will be a good way to tell. Experiment. Try plugging in numbers and seeing how many answers you get for y. Right. But if you just want to get the answer as quickly as possible, this rule should work for you for this class. All right. So determine whether the following equation defines y as a function of x. So there you see that phrasing. So I guess maybe the author addresses it a little bit. And maybe, I don't know, I've been using Math Excel. I haven't really looked at the print version of the textbook. Maybe I need to revisit that, and maybe that topic is addressed more than I think it is in that textbook. But like all of these rules, all of these questions are to determine if y is a function of x. All right, so you could use the shortcut, and that's going to give away the answer right away. Is y inside an absolute value? No, it's not. Is y being raised to an even power? Yes, it is. So this will not be a function. Now, by conducting an experiment, we can actually find out why that causes it to not be a function. So what we can do is pick a number for x. I would highly recommend that you avoid getting 0 in any capacity when you're doing these experiments, because 0 has a tendency of wiping things out that you would otherwise be able to see. So I would not choose 0 for x here. If you choose 0 for x, you will not get to see why it's not a function. It'll actually behave like a function would when x is 0. That's the only number where it behaves like a function. Everywhere else, it's not a function. It doesn't behave like a function. And like I said, all it takes is one example showing that it doesn't behave like a function, and the whole thing gets labeled as not a function. But the point is, don't choose 0 here. So we will choose 1. 1 actually works out pretty nicely. So you pick a number for x, you plug it into the equation, so we get 25 times 1 squared equals y squared. Continue up here. Well, I guess I'll do this here. 1 squared is just 1. 25 times 1 is 25. And then I'm going to solve this for y. How do I get y by itself? Well, I have to cancel out that power of 2. And to cancel out a power of 2, I take the square root. But we learned back in chapter 1 that when you take the square root of both sides, you have to do plus or minus. So we get square root of 25, which is 5, but we will have both positive and negative 5 as my answer for y. So y actually equals 2 different numbers, right? And so we have positive 5 and negative 5, so I don't know why I'm putting an arrow there. Sorry, my phone's ringing, which is kind of weird because nobody ever calls me. Undo that. Whoops. Okay, let's do that negative sign again. What I want to say here is there's 2 y's, right? So we have 1x, 2 different y's. So I already wrote it down. I'll just point to it over here. So it's not a function. So that's how you would determine if an equation is a function, by experiment. Plug a number in for x, solve it for y, see how many answers you get. And if it behaves like a function when you do the experiment once, then you should test it again, at least one more time. And if it behaves like a function again and seems like it will always give you one answer for y, then maybe it's pretty safe to call it that it's a function. But all it takes is one example of it not behaving like a function, and we're done, right? So I don't need to test it again to see, well, what happens when x is negative 1? I already have determined, because it's just one bad apple, right? It's here I'm getting 1x with 2 different y's. That's not a function, and that's all it takes is just one example of that to show the whole thing is not a function. What about this equation down here? We have x is equal to the 13th root of y. That is awful, right? Is this a function? I always like to poll my class on this, and usually it's about 50-50. Like half the students think it is a function and the other half think it's not. And they're just basing it on, like the ones that say it's not a function, they're basing it on, that just looks like a bad equation, right? It's kind of scary looking, and functions are nice things, right? So if it looks scary, it can't be a function. But this is a function. So you don't want to judge whether an equation is a function based on if it looks like a nice equation or a hard equation, right? Is y inside an absolute value? No, it's not, right? It's inside a radical, but that's not an absolute value. Is y being raised to an even power? No, it's not being raised to an even power. So because it's not one of those two things, this will be a function. But again, we could do an experiment to test that out. Sorry, this is supposed to be an arrow. It's just really poorly drawn, and I'm making it worse. Let's erase that. I'll just not put an arrow at all. So let's do an experiment, and let's choose x equals 1 again, right? So I'm picking one value for x. I'm going to plug it into this equation, so I'll get 1 equals the 13th root of y. Now, how do we cancel out a 13th root? So square roots cancel out with powers of 2. So to cancel out a square root, I raise it to the second power. We saw that back in chapter 1 also. Cube roots cancel out with powers of 3. So a 13th root, following that logic, only cancels out with a power of 13. So we actually, to cancel out that 13th root, we have to raise this to the 13th power. If we do that to the right-hand side, we have to do the same thing to the left-hand side. 1 to the 13th power is still just 1. Here, the 13th root cancels out with the power of 13, but there's no plus or minus. You only do plus or minus if you take the square root of something squared. Then a plus or minus needs to be used. Or the 4th root of something to the 4th power. Even powers like that. But you never do a plus or minus if you're just raising both sides to some power, even if it's an even power. So if I was raising both sides to the second power, you still don't do plus or minus. It's only when you do radicals, when you do square roots or fourth roots, right? And so we're going to get y equals 1, which is just one answer for y, right? So 1x, 1y. You could test it again, right? You could try, x equals -1, for example. Plug that into the equation. And again, to solve it, we raise both sides to the 13th power. We get -1 to the 13th power. Because that's an odd power, this will be -1. Here, the 13th root cancels out with the power of 13, and we get y is equal to -1. So 1x, 1y, right? And it appears like that will happen every time. Now, if we pick a different number like 2 or 5, and you raise that to the 13th power, you're going to get big numbers as a result. But it will still follow the pattern of I choose a number for x, I get one answer for y. That's going to happen every time. So this equation is a function. All right. We have a couple more topics to talk about in section 2.1, domain and range, which we will actually spend quite a bit of time dealing with in a large part of chapter 2 and also in chapter 3, and pretty much any time we're doing kind of graphing. So we introduce the concepts here, and so I don't know, how do I want to say this? This material is easier when you're looking at a graph. Once you have a graph set up, then finding the domain and range, I have a pretty nice method of doing that I think you'll find pretty easy to follow. But we're not there yet. We're not going to do any graphing in section 2.1. And so we're going to talk about finding the domain and range by just analyzing the equation we're given. And that can be a little more challenging. It's nice when you have a visual to look at. It's a little more difficult without that visual, but we'll talk about how to do that in section 2.1. But I just want to caution you that this will probably get easier for you once we start graphing, because then you can figure out the domain and range from the graph. Now, maybe that's the wrong way to think of it, because maybe you want to know the domain and range first before you draw the graph to help you make the graph more accurate. But I kind of approach it the other way. You graph it first, make sure you know what the graph looks like, the right shape, the right points. And once you're sure you have a correct idea of the graph, then the domain and range can be found from the graph. The domain of a relation, it doesn't have to be a function to have a domain. The domain of a relation is the set of all values that x is allowed to equal. Right? So, and that's your independent variable, right? So I'm just using the label of x to represent the independent variable. The domain is all possible values of the independent variable. So in general, that would be the x variable. So what are all the numbers that x can equal? That's the domain. And I think students don't really have difficulty with the concept per se. I think, this is just my theory, I haven't really tested it or anything, but I think the difficulty that students have with the domain, because it is a challenging topic for a lot of people, is the precision with which we have to state the domain. We cannot just estimate the domain. We can't give a ballpark estimate of, oh, the domain is pretty much all these numbers. It has to be exact. We cannot include a number in the domain that shouldn't be there. Not even one number that shouldn't be there can be accidentally included. And we can't accidentally leave out a number that needs to be there. We have to have it down to the last number, everything that we could plug in for x. That's what the domain has to be. And we have to get it exactly right. That's where I think people start to have trouble. The range is the same idea, but for the y variable. The range of a relation is the set of all values that y is allowed to equal. So anything that you could get as an answer for y. So usually I like to think of it that way, right? You're picking numbers for x and you're getting answers for y from your equation. So in that regard, the domain is any number you're allowed to plug in for x. The range is any numbers that you could get as answers for y. You want to know what all the different possible answers are that you could get for the y variable. That's the range, right? But again, has to be precise, down to the last number, anything that y could possibly equal. All right, so that's domain and range. Now, this one's actually going to be pretty simple, I think. So the domain, we want to find the domain and range of this relation, and this is a weird one. You don't normally deal with relations in this form. It's a collection of points. So it's a relation. Each point is relating an x value to a y value. But you could also think of this as a table. So if that form bothers you, feel free to just restructure it as a table. right? This is 9 comma 7. X is 9, Y is 7. This is 24 comma negative 8. This is 39 comma 7. This is 9 comma 3. And this is 54 comma 3. All right. The domain is anything that X could possibly equal. And for this relation, it's any number in this column would be, so I shouldn't say any number, any number in this column should be in the domain, and any number not in that column should not be in the domain. So the domain as a set should be all the numbers that are in this column. Right, so my domain would be all possible values for X. And because we have just specific numbers to list out, we set up the domain as a set. So we use this curly brace, and then we just list the numbers that X is allowed to equal in this set. X can equal 9, so I'll put that first. X could equal 24. X could equal 39. And X can equal 54, and that's it. So even with these tables, so an example I will often give students, and I don't think they're going to try to trick you like this, but if you have like 0, 1, and 2, and this is like, let's say 3, 4, 5, right? So there is apparently a pattern there, it looks like, right? So you might say, well, and so let's say that's your relation. That's it. That's your relation right there. I could maybe ask you, if X was equal to 3, what do you think Y would be? And you would say, oh, it looks like it would be 6. You can't ask that question. If you're told this is your relation, that's all there is to it. X is not allowed to equal 3. In this relation, the domain is 0, 1, and 2. And that's it for X. That's the only numbers X is allowed to equal. You're not allowed to speculate that if the table were extended to a further value, that this is what Y would equal. You're not allowed to speculate that. I mean, I guess you could speculate, but that's not part of the relation. And it is actually maybe even the case that X, even, you don't know the background to these numbers, right? It may not even be possible for X to equal 3. So an example I will often give is like I do something a little more than this. I do like, 0, 1, 2, 3, and 4, and then put some numbers over here. And then I say, well, you might think, oh, because of the pattern here that when X is 5, Y would equal this. But what if I told you that X is representing the ratings of different restaurants, and that the highest rating you could get is a 4, or the ratings of different movies. So you could give a movie 1 star, 2 star, 3 stars, or 4 stars, or you could give a movie 0 stars, but 5 isn't an option. So then in that case, even if there is a pattern here, X could not equal 5. That wasn't a possible value for X if I tell you the background information that X is representing the number of stars that we rate a movie, right? And so you're not allowed to speculate, right? What you're given is all there is to that relation. So in this relation, you might say, well, what about when X is equal to 8? It's not allowed to equal 8. It's only allowed to equal specifically these numbers in this list, right? Same thing for the range, right? The range are all the possible values for Y, which means it'll be all the numbers in this column here. Don't repeat. I guess I didn't really point that out here, but 9 occurs twice, which means this is not a function, right? Because we have repeating values of X. 9 occurs twice, but you don't want to write it twice in the domain. So when you write the domain in range, there should not be duplication. Each number is listed once. So for the range, and I don't know if these have to be in numerical order. I know that when you look on Math Excel at the answers, they will put them in numerical order for you. But I don't know if it has to be that way in order for it to be correct. Because with sets, there's really no requirement that sets have to be in numerical order. And so I'm tempted to just say this: 7, negative 8, 7's already on my list, and then 3. And then 3 happens again, but we don't list it twice. And so this would be the range. These are the only numbers that Y can possibly equal. And hopefully Math Excel would be okay that they're not in order. Okay, what about if it's an equation? Determine the domain and range from this equation. This is going to be a little more difficult to figure out. So what you want to look for anytime you're asked for the domain and range is you want to look for limitations. So really my thought process is this, and I don't know if other math teachers think of it the same way, but I approach this problem as with the assumption that the domain is all real numbers and the range is all real numbers until I find evidence to the contrary. So start with that assumption that your domain and range will be all possible numbers, but then look for limitations in the equation. And if you find any limitations, then you adjust the domain and range accordingly, right? So for this particular equation, we have x plus 7 equals the absolute value of y. What do we know about absolute value? Absolute value, I want to say always positive, but then, like I said, now my paranoia, another math teacher is going to watch this video and say, no, it's not always positive. That isn't right. Could be 0, which isn't positive, right? So again, technically, no, it's not always positive. The proper way for me to say that is this is never negative, right? It's either 0 or positive. That way, math teachers don't get mad at me. Okay, so absolute value, the output from that, so once we take the absolute value of a number, it will never be negative. If the right-hand side of the equation is never negative, that means the left-hand side of the equation can never be negative either, right? Because these have to be equal. They have to match each other. So if the right-hand side can never be negative, then I can't let the left-hand side ever be negative either. And so x plus 7 is never negative in this equation. It cannot be allowed to be negative. So how can I write that mathematically, never negative? Well, that means it has to be bigger than or equal to 0, right? So I meant to change colors there just to make this a little bit easier to read. It has to be bigger than or equal to 0 for it to never be negative. So x plus 7 has to be bigger than or equal to 0. What does that tell you about x? So you might say, why are you writing all this? So if I've identified that limitation, that x plus 7 can never be negative because then it will never match the right-hand side of the equation, that's a limitation on what x is allowed to equal, right? I have to be careful what I choose for x to make sure that x plus 7 never comes out negative. So for example, I can't choose negative 8, right? If I choose negative 8 for x, I get negative 8 plus 7, which will be negative 1. That's negative. It'll never match the right-hand side. The equation won't work. And so I can't choose negative 8 for x. I can't choose negative 9. So I'm trying to decide what numbers could I plug in for x and still meet that limitation, still meet that requirement. And so that's what I'm doing here. Now you can probably guess, right? How low can I go with this before it's negative and I can't go any lower? It's negative 7, right? I can choose negative 7 for x and I would get 0 here. And that's as low as I can take this before it becomes negative. And so if you figure it out that way, that's fine. That x can only go as low as negative 7. But this is another way to approach it. Convert it to an inequality and then solve it for x and then let the inequality tell you the answer instead of you having to figure it out, right? So you subtract 7 from both sides to solve this for x, and we get x is greater than, that's a horrible greater than, let's try that again, greater than or equal to negative 7. And that's my domain, right? Because the domain is what is x allowed to equal? X has to be a number bigger than or equal to negative 7. It cannot be lower than negative 7 in this equation, right? So my domain, and what you will often want to do with domain, especially, so I can't do this like we did in the last problem. Sorry, that was a horrible drawing too. We can't do it like this because what am I going to put? That x has to be negative 7, negative 6. You might think that's okay, right? This is just, these are numbers that are bigger than negative 7, right? Negative 5, negative 4, etc. But I'm skipping a whole bunch of numbers, right? What about negative 6.1? What about negative 5.1? What about negative 4.392, right? These are numbers that are bigger than negative 7, so these are also possible values for x. We can't leave these out because, like I mentioned, the domain is precise. We have to include every possible number that x is allowed to equal. And these are numbers that we would never choose for x, but it is possible for x to equal these numbers, right? It would be okay if we did, right? These are numbers that x is allowed to equal, even though we may never have chosen those numbers when working with the equation ourselves. And so this is not going to work. What you want to do is what we did back in chapter 1, again, using some skills from that chapter, is write this as an interval, which for me, to help me write this as an interval, I like to see what the graph looks like. And I'm not graphing this equation, I'm just graphing the domain here. That x has to be bigger than negative 7 or equal to, which means I put a bracket on that. And as an interval, that's going to be from negative 7 to infinity. Brackets on the negative 7. So that will be my domain for this equation. What about the range? For the range, I'm looking for limitations on the y value, but there aren't any. Now you might say, wait a minute, we said it can never be negative. The output from the absolute value is never negative, right? This part is never negative, not this part, right? What about the y value itself? Does that always have to be positive? No, we can plug negative numbers into an absolute value. For example, I can plug in -1 for y, and then the absolute value of -1 comes out +1. That's fine. And I can get the left-hand side to equal that 1, right? If I choose -6 for x, -6 plus 1, sorry, I said the wrong number, -6 plus 7 gives me 1 also, and so the left-hand side matches the right-hand side. So y can be negative. The absolute value has no problem taking negative numbers as an input, but it never produces a negative number as an output. That was the limitation, is that once you take the absolute value, the numbers will never be negative at that point. But as for what numbers we can plug into that absolute value, anything goes. Positive, negative, fractions, big numbers, small numbers. I can plug anything I want in here for y. Sorry, that came out kind of weird. But the answer, the result I get on the right-hand side after I take the absolute value will never be negative, right? But the y value itself can be anything. There's no limitation. So there's no limitation on what goes into the absolute value. So if there's no limitation, we just keep our default answer, which is all real numbers, which we write as -∞ to infinity, right? So if you think about, if you were to graph all real numbers, I guess maybe I should have wrote that out first. So all real numbers was the assumption we started with, right? That we assume the range is all real numbers until we find evidence to the contrary, but there was no evidence to the contrary. There were no limitations. So we're going to go with that assumption that the range is all real numbers. As a graph on the real number line, it would go forever to the left, forever to the right. So it would be, everything would get shaded in for all real numbers. That's going to be from -∞ to +∞. So that's why the interval looks like that. Okay. I think we have one more topic here. Okay, one more example of that. And then we have function notation. So we're almost done. Determine the domain and range of this relation. So why don't you pause the video and see if you can determine what the limitations are in this problem. I'll give you a hint. Both the domain and the range have a limitation this time. So neither answer will be all real numbers. And then once you've made a guess at what you think the domain and range is, resume the video and see if you came up with the right answer. All right, so sorry, there's probably a lot more work on here than you expected to see. The answers you should have come up with are here and here. So the domain for this function, this is actually a function, is 7 to infinity. The way you arrive at that conclusion is to realize that inside the square root itself, you don't want negative numbers. Now maybe that might be a little bit confusing to you because we talked about how to manage negative numbers in a square root. But what's the result when you take the square root of a negative number? It's imaginary. And for the purposes of defining the domain and range, which are related to like graphing, you don't want imaginary numbers, excuse me. So there's no room for imaginary numbers when we're doing our graphs, so there's no room for imaginary numbers in the domain and range. So we have to avoid getting negative results inside the square root. So I don't want to pick numbers for x that would make this come out negative, because then the square root's going to come out imaginary and it messes everything up. So how can I make sure this doesn't come out negative? I want to make sure x minus 7 will stay above 0, right? Greater than or equal to 0. It can go as low as 0, but I just don't want it to be negative. And then I can solve that for x, and it tells me that x has to be bigger than 7, which again, you might be able to tell by just looking, right? And so that's how we got that. Now, once you get a number inside the square root that's not negative, because that's the limitation on x, then when you take the square root of that not negative number, the answer will not be negative, right? You never get a negative result from a square root, right? So the square root itself is never negative, which means, and since y equals that square root, y will never be negative, which means y will have to always be bigger than or equal to 0, which means the range will be from 0 to infinity. All right, so that's how we got the domain and range there. The last topic here is function notation, which looks like this. F of x is how you would read that. It is not f times x. Do I have that screen here? No, I used to have like a screen of like what to make of this notation. It's not multiplication, even though it looks like it would be. And that's unfortunately misleading. This is just the y value. It's the y variable, excuse me. So if you have an equation that is a function, like let's say this, right? Y equals 2x plus 3. That's a function, right? I can replace the y variable with f of x. And now I can write it like this. F of x equals 2x plus 3. Now you might say, why on earth would you want to take a simple thing like the y variable and replace it with this horrible looking thing, f of x? There's multiple uses of this function notation. One thing is that it allows us to give these equations a label. So if I had a second equation like y equals 3x plus 2, right? That's also a function. I could replace this y with function notation also, but I could pick a different letter. I don't have to use f. I could call this one g of x equals 3x plus 2. And now I've given a different name to these two equations. So if I want you to plug in a number to one of these equations, I don't have to say, oh, use that first one over there or use that second one, which might even be confusing. I can identify it based on its label. I could say use function f or use function g, and you'll know exactly which equation I'm talking about. So, and what's nice is it builds that name directly into the equation itself. So it doesn't have to be external to it, because if I'm not using function notation, I would have to do something like this, like this is equation 1, this is equation 2, which is external to that equation. Function notation builds the label directly into the equation itself. And so, and I guess furthermore, the thing in the parentheses is there for information only. It is not there mathematically. So the analogy I like to give that I think helps students understand what to make of this, it's like a pop-up window, which I know a lot of people have pop-up blockers and you never see pop-ups anymore. But imagine this as like a pop-up window that you can just minimize. It's only there for informational purposes. It's not there mathematically speaking. And it's there to let you know what number is getting plugged into the equation, if there's a number there, or what variable to expect to see on the other side of the equation. So by seeing an x here, I know that the independent variable is x, and that's what the rest of the equation is going to pertain to. Not that we're going into this topic at all, but like you could have functions with two variables like this, right? And if I say you have f of x comma z, that lets you know, without having to even look over here yet, that you're going to have to deal with two variables on the right-hand side, x and z. So you're going to have some equation over here with those two variables, right? So that's kind of the information that it provides. So let's go ahead and look at an example, right? So we have g of x equals 4x plus 2. Find g of 3. So what they're telling me to do, and this is what's so awesome about the function notation. There's so much, it's so compact. There's so much information contained in just that little bit of symbol, right? It tells me which equation to use. Use equation g. Not that I had other choices here, but I know which equation I should use. It tells me what to plug in for x, right? They want x to equal 3. They didn't have to like spell it out for me. It's built into the notation. And they're asking me to find this, but remember, this is the y value. So really they're asking me to find what y is equal to. So think about all of that information is being contained in this tiny little package. Use equation g, plug in 3 for x, and find the answer for y. That is what it's asking me to do when it says find g of 3. Right? So instead of having to write all those words out, it's all contained in that little bit of notation. Right? So what I'm going to do is take g of x, which is 4x plus 2, and I will replace the x with 3 because that's what they did in the function notation. I do the same thing on the right-hand side of the equation, and I'll get 12 plus 2, which is 14. Right? And let me kind of back up there a little bit. So I'm going to copy this down, and I get g of 3 is equal to 14. Now, some students will look at this and say, but I need to get g by itself. And they'll think to finish solving this, they have to divide by 3 on both sides. But then you're running afoul of the thing I said earlier, which is it's not there mathematically. This is not multiplication. It's not g times 3. So dividing doesn't make any sense, right? If this is not multiplication, why are you dividing? It's not really there. Right? This is a ghost. It's a pop-up window, and we can just minimize the 3 if we wanted to. G already is by itself, is the point that I want to make there. right? The 3 is not really there mathematically. So you already have g by itself. G is equal to 14. 3 is only there to let you know what you plugged in for x to get that result, right? X was equal to 3. That's how I got 14. Okay, now the second example here flips things around on you, so be careful, because a lot of students blindly, oh, there's a number, I'll just plug that into the equation and get my answer. But it's the other way around, right? Find x if g of x is equal to negative 23. So here, they're giving me the y value. Y is equal to negative 23, and I'm supposed to solve for x. Right, so again, this is my y value here. G of x is y. They're telling me that's equal to negative 23, and then I copy down the equation, and I'll solve this for x to find x when y is negative 23. Right, so it's the flipped around version of this one. Here they're giving you x, and you're trying to find y. Here they're giving you y, and you're trying to find x. Right, so I'm going to subtract 7 from both sides. I'll get negative 30 is equal to 6x. Divide by 6 on both sides, and I get x is equal to negative 5. And that's the answer for that one. Okay. Oh, I keep thinking, oh, this will be the last one, but it just keeps going. So two more slides here, and then we'll be done. And this is a doozy of a problem. So not only can you use function notation to indicate that you want to plug in a number, you can use function notation to indicate that you want to plug in an entirely new variable or variable expression, which is what they're doing here. So g of x is equal to 2x squared plus 5x plus 10. They want me to find g of p plus 4. So again, notice the substitution there. They've replaced x with p plus 4. So we want to make that same substitution in the rest of the equation. So everywhere I see an x starting with the function notation, I'm going to replace it with p plus 4. I do that here, but I have to do it throughout the rest of the equation as well. So this x becomes p plus 4, and then that has to get squared, plus 5 times this x becomes p plus 4 plus 10. Right. And then, unfortunately, Math Excel isn't going to let you get by that easy with saying, okay, that's the equation. They want you to simplify this, so we have to multiply all this out. P plus 4 squared, remember you can't distribute the power of 2 there. You have to write it as p plus 4 times p plus 4, and you have to FOIL. So we'll do first, outer, inner, last. We get p squared plus 4p plus 4p plus 16. And then that has to get multiplied by 2 plus 5 times p plus 4 plus 10. I'm just going to copy down the rest of this. Then we'll distribute to get rid of all these parentheses. So I'll distribute the 2. We're going to get 2p squared plus 8p plus 8p plus 32. When I distribute the 2 to all of those. Here we'll distribute the 5. So we get 5p plus 20. And then the plus 10 just copies down. And then we're just going to combine like terms. So we'll get g of p plus 4 is going to equal 2p squared. There's nothing to combine that with. 8p, 8p, and 5p is going to be 21. So we get 21p. And then 32, 20, and 10. That's going to be 30 plus 32, which will be 62. And we get this new looking equation, which is based on the old one. So we've basically just converted it from the variable x to a new variable p using that substitution. All right. And so that would be the answer there. Now, what is this last problem about here? And it's really hard to see. I apologize for that. I wonder, can I zoom in? Yes, I can. Okay. So let's zoom in here. The amount spent online for computers in the year 2000 plus n can be modeled by the function c of n equals 0.93n plus 5.8, where n is a whole number and c of n is, and that's the function notation there, is billions of dollars, right? So if c is equal to 5, that's $5 billion, right? And n is just the number of years since 2000. So for 2005, n is 5. For 2020, n would be 20, right? What does c of 4 represent, and what is it? So what does it equal? So c of 4 is going to equal, let's see, the amount spent online, for computers in the year 2004, right? Because here n is equal to 4, so that's 4 years since 2000, so it's going to be 2004. So the year is being determined by this number, and C, as its definition, is the cost, or not the cost, I keep thinking it's cost because it's C. It's the amount spent online for computers in that particular year. So when I find C of 4, the number I get there is how much money was spent on computers in the year 2004. So that's what it represents. What is it actually equal to? So we'll take C of n, which is 0.93 n plus 5.8. I'm going to plug in 4 for n, so I'll get 0.93 times 4 plus 5.8. And I'm going to need a calculator for this, and my phone was buzzing earlier, so I know it's nearby. So that's right here. And so I'll get 0.93 times 4 plus 5.8. And so I get that C of 4 is equal to 9.52, which tells me that in the year 2004, $9.52 billion were spent on computers online. Okay, so that's part A. Fortunately, we have a part B, and then we can finally be done with this video. I'm sorry it took an hour to get through this material. Find the year in which online spending for computers will reach 13 billion. I don't know why that's italicized, but so here it's the flipped around version of part A. They're giving me the amount spent, which is C. So C of n is going to equal the 13 billion, which remember, C is in billions already. So we just need C of n to equal 13, and that means 13 billion. And we want to solve that for n to find what year that would be. And so for part B, and they give you a graph over here. You can see it's a function because if you do the vertical line test, but I wouldn't use the graph to answer these questions unless it specifically said to do that. You're going to get a more exact answer from the equation. So we want to plug in, so we have C of n equals 0.93 n plus 5.8. C of n is equal to 13 for part B. So we plug in 13 for C of n. So again, this is a case where they're giving you the y value, which in this case is C of n, and you're solving for the x, which in this case we're calling n. All right, and so let's go ahead and solve that equation, and then we can be done. So minus 5.8 from both sides. And so I use my calculator, 13. I should be able to do this in my head, but when I get to the end of these videos, I start to mentally fall apart and I can't do any even simple calculations. So I get 7.2, and then I divide by 0.93. And so I'll get a decimal number. And if you look at the directions, I don't know if it was on here. It doesn't say actually, but the direction should tell you if you're going to get an unpleasant answer like the one I just got. It'll tell you how far to round it, I think. So I got 7.741935548 as my value for n. And so, whoops, that was definitely the wrong button. Scroll down a little bit more. So again, the question was, what year will it reach 13 billion? And so I guess we don't have to even really necessarily round this. This is, when n is equal to 7, that's 2007, right? So if n is equal to 7, that's the year 2007. So it wants to know the year. It doesn't want to know what n is equal to. So I lost track of that myself, right? So I won't have to round in this case because it's not asking what does n equal, which would be this horrible number. It's asking what year are we hitting 13 billion? And it's going to be 2007 because it's not 2008 yet, right? And so it'll be in the year 2007, even though the 7 here would make you want to round up. And you might check. Maybe MathXL does expect you to round this to the nearest whole number, in which case the answer would be 2008. But my argument is it'll already have passed 13 billion by the time you hit 2008. So I think it's going to be happening in 2007 in that year before it reaches 2008. So since you want to know what year it's going to be when it surpasses 13 billion, it's going to happen before 2008 because we haven't hit 8 yet for n. And so it's going to happen in the year 2007. So I'm guessing that this would be the correct answer rather than rounding this up to 8. I think it happens in the year 2007 before you reach 2008. But I would say view an example on the homework for that and just check to see if that's the rationale they use, or if they rather you just round the number first and then use that as your result. Either way, it's going to be near the end of 2007, just before 2008, and either answer is a pretty good estimate for when it's going to hit 13 billion. I won't belabor that point any longer because I know you're ready for this video to be over, and so am I. So thank you for watching this lesson on section 2.1. I will see you in the next video for section 2.2.